Madhukar madam, should we start?
Good evening, all. On behalf of Marathwada Mitra Mandal and Department of Electronics and Telecommunication Engineering, I welcome you all for Faculty Development Program. So it is my great pleasure to introduce to you today's distinguished resource person for this FDP Faculty Development Program. So we are honored to have with us Dr. Rajesh Singh sir. Dr. Rajesh Singh sir received his PhD degree from in microwave engineering from IIT Delhi. Currently, he is working as assistant professor at Department of Electronics Engineering in DIIT Pune. He has worked as an RF consultant at Iran Energy Private Limited, New Delhi. He was postdoctoral researcher at Microwave and Radiation Laboratory, Department of Information Engineering, University of Pisa, Italy. His research interest includes active integrated antenna, RFID, EMIMC, wireless power transfer, reconfigurable 2D and 3D antennas for current and future wireless systems, smart gloves for near and far field, ultra high frequency radio, RFID, SSPP, and antenna modules for automotive. Uh, he has authored and co-authored more than 55 international journal articles and conference contributions. He is an active reviewer of various reputed journals, including IEEE TAP and AWPL. He served as a chairman for period 2016 to 2018 and treasurer for period of 2014 to 2016 of IEEE MTTS Students Branch Chapter at IIT Delhi. He is a recipient of Young Scientist Award from International Union of Radio Science, General Assembly and Scientific Symposium 2020 and Distinguished Service Award for RFIDTA 2019. So we have actually a very great person with us. And throughout our session, Dr. Rajesh Singh sir will be giving us the hands-on session on simulation of passive microwave components, which will provide invaluable knowledge to us. So I think we are sure that this session will be very insightful and inspiring for all of us. So without, I think, further ado, let us start with the session. Welcome to the session, sir.
Yeah, thank you, ma'am. Good evening to all. Thank you very much for introducing me in front of the audience.
Yes.
Uh,
Let us start,
yeah,
sir.
yeah, I shared my screen.
Yes.
And yes. Okay, so first I would thank the organizers, coordinators and co-coordinators, or maybe other people who are involved to organize such beautiful events, because it is beneficial for all, and it is they are conducting after the working hours, so it is actually better. The topic of this talk is hands-on session on simulation of passive microwave components. As we know that this topic is actually very broad, but still we will try to cover some basics of passive microwave components. Then we will go for hands-on session. So hands-on, initially we thought that you may use your laptop, then we can conduct some hands-on, but it may take more time. So I will show you some simulation on CST, that how it is happening. Then maybe we will share the link. You may download the CST software and you can do in your systems. So that would be better in that short time. So I'll cover how we go to the planar transmission lines from the 3D lines. Then we'll cover some passive components. Those are the basic building blocks for the microwave transceiver systems. So that we will discuss maybe in detail: microwave filters, couplers, power dividers, then phase shifters. Then probably antenna we will discuss very little, because tomorrow is another session. There we can discuss this antenna part. So we know that if you see in this slide, the left side, we are having this coaxial cable. This coaxial cable, outer side, there is a conductor. Inner also there is a conductor. In between, there is a dielectric. So when we see the cross section of a coaxial cable, it look like this. Okay. So this cable is actually 3D. So the technology earlier which we had, it was 3D technology. So most of the components, if you see waveguide based components, all are 3D components. But now as research is evolving and people are going for more compact circuits, so now we have this planar circuits. So we will discuss in this session mostly planar circuits. So when this 3D line, when we compress, just think that if we compress this line, we will have this kind of a structure, and if we remove metal from here, so this structure will become in this shape. So outer side there is a ground plane on both sides. In between there is a center conductor. So this line is called a strip line. So in this strip line, you can see there are top side and bottom side, both are metal, which is ground plane basically. In between, there is a small strip, which is the, when we feed the RF, then the center pin will take that RF and the ground will help in returning that signal. So what are the field strength? We know that if one metal is there and another metal is there, then electric field lines will go from the center conductor to the ground side. And both side there is a ground, so both side these electric field lines will go. Similarly, if we see the magnetic field, then it is in the round and orthogonal to the E field. So E and H will be orthogonal to each other. And if we take a E and H cross product, then you will have the feeding which will go inside this center conductor. So this is the basic concept of coaxial cable or maybe other cables. So now we have moved from 3D coaxial cable to the strip line. So why we are saying this, it is planar, because the third dimension which we are seeing in the height, it is actually very, very less. So we treat this dimension is very less than lambda. So we call this line as a planar line or 2D line. So, but the problem with the strip line is handling issue. So this is the circuit. It is based on the strip line. So what is the problem in the strip line? Suppose you have any component. So these are the tracks. We will discuss what are these tracks. So as of now, just think that some substrate is there, some thicker and thinner tracks are there, and some connectors are connected. So the problem of strip line is you have to cover this whole part, because both side we have metallic enclosure. So this enclosure you want. So the problem is, suppose some problem is there in this, maybe this is simple passive network. If this is an active network, then there will be a more issue. Suppose you want to remove some lumped component from the circuit L and C, or it may be device like FET, BJT, then there will be a problem. You have to remove first this cover, then only you can do some changes. So this technology, there are some advantage of this technology, but still it is not in use, very much use. Okay. So what is the solution? Again, this strip line can be converted into microstrip line. So what we are doing here, we are just removing the top part, top ground part. So we have just metallic strip, small thickness strip, and then you have ground. So this is the structure. Field lines will be more or less same. Electric field lines will go from center pin to the ground, and it will go from here to here, because all field lines will go terminated into ground. So there is no outer conductor at the top side. So these field lines will go in the air and again terminated into this ground. So this is the concept when we have microstrip line, which is generated again from the strip line. So this is the microstrip based component. So this is just one example we have just taken. One switch is there. So this is the connector, coaxial connector, where we will feed RF. That side maybe we can receive that RF. Here you can see there is a dielectric. So this PCB is having some dielectric constant. It looks like this. And there is a track 50 ohm line, and there is a one component is connected. It may be anything. It may be lump component like L and C. It may be any active device. But from this picture, we can understand very easily that if we want to handle such components on microstrip line, it is very easy. You can just desolder it, remove it, you can replace the components. Also, this microstrip line is useful to feed, not only for this feeding, it may be useful for some practical applications like transmitters and receivers. Okay. So transmitter will have like power amplifier, then it will have some mixer and then antenna. So all these parameters or all these components can be integrated on a same PCB. So this is the usefulness of microstrip based component. So people are using microstrip line for practical use. Now we see in general what are the differences in the microstrip and strip line. Okay. So we will discuss few parameters like propagation constant, that is lower. Lower means waves move faster in the microstrip line, where strip line waves move slower. Okay. So this is not the major factor. The major factors are radiation losses and dielectric losses. So dielectric losses in microstrip line is lower because the field lines, those are going from center pin to the ground, and it is having less dielectric compared to the strip line. But the radiation losses are more because this circuit is open. A strip line, we know that it is closed, so radiation losses will be less. So this is the advantage of a strip line. When we want more and more directivity, then we have to use a strip line. Okay. Low loss circuits are made from a strip line. If we talk about the trace width is actually, we normally take 50 ohm impedance. So 50 ohm line, when we make, if we calculate the width of that line for 50 ohm, it will be twice of that strip line width. So width is more in case of microstrip line. So strip line can be thin compared to the microstrip. So shielding, if you see, shielding is lower in case of microstrip line based on this enclosure, and it is high shielding in the case of strip line. So these are the general parameters where we can see some differences in the strip line and microstrip line. So these strip line looks like this, microstrip is this, where one more line is used, coplanar waveguide, CPW. So this CPW line is having center conductor and both side there is a ground plane. Okay. So both side there is a ground plane means you have all these three metals at the one layer. So there is nothing in the back side of this microstrip or this dielectric. Okay. So what one more variation is there in the CPW, grounded CPW. So at you may also find the line which is having ground here also. Okay. But the concept is signal is traveling through this center conductor, and the field lines will go from here to here and here to here. So your power will flow along the strip line. Okay. So this CPW is useful when we are at high frequencies. Why it is useful at high frequency? Because it is very difficult to make shunt components. Shunt components, like suppose you want to make a low pass filter, then you have series inductor and shunt capacitor. Series inductor, it is easy. We will see that how we can make an inductor, but it is very difficult to make shunt capacitor. We cannot make via. We cannot make hole at high frequencies. So this is that if you want to make a capacitor, you can directly connect a capacitor in between the signal and the ground, so that we can easily achieve shunt components in the case of coplanar waveguide. So it is very useful at very high frequencies. So strip line, if we see in there are some parameters, phase velocity will be there, guide wavelength is there. So guide wavelength is actually related to the free space wavelength. So free space wavelength we can easily calculate by C over lambda. But there is a guide wavelength which is different from the free space wavelength. So whatever wave it is traveling in air, if we pass the same wave in a dielectric, then speed or the guide wavelength will be different. It will be lower. And what is the parameter that lower the guide wavelength? It is the epsilon r. It is the dielectric constant of that substrate. If dielectric constant is very high, then guide wavelength will be less. Also, one more parameter which is very important is the characteristic impedance. Characteristic impedance of the line is the impedance is the ratio of voltage and current, but your line should be infinite. So this characteristic impedance definition is quite different. It is not like input impedance, V over I. So this impedance is again V over I, or you may treat as E over H, electric field over magnetic field. But consideration is line should be infinite. Infinite means there should not be any reflection. Then we call that impedance characteristic impedance, which is quite useful parameter. So characteristic impedance and propagation constant are the two parameters which we consider for the planar lines. So this is the basic configuration as already discussed, that strip line, there is a strip, metallic strip, backside there is a ground plane. So very easy to convenient to mount discrete devices. Discrete devices like some components, L and C components, or it may be devices like active, okay, BJT, FET. But the one more challenge in the microstrip line is quasi TEM mode is propagating. Okay. We know that in coaxial cables, TEM mode is propagation. What is TEM mode? Transverse electromagnetic mode. So electric field and magnetic field are in the orthogonal, and both are orthogonal to the propagation direction. But in the microstrip line, there is another mode which is traveling with that dominant mode, TEM mode, that is called surface wave mode. So this surface wave mode come in the microstrip line because of the discontinuity in the field. So when signal is traveling from here to here, it will face two dielectric. One is the air, another is the dielectric. But it doesn't happen in case of coaxial cable or strip line, where there is no air inside. So because of the two different dielectric media, we have one more mode which is traveling along the line. So we call this mode as a quasi-TEM or TEM-like mode. Dominant is TEM, but still there will be a small component which will take small power in that mode, so it will be waste. So directivity in the case of microstrip lines are lesser than the strip line. So due to mismatch of velocity of propagation at the interface between air and dielectric, we have quasi-TEM mode. Again, microstrip line, if you want to make a microstrip line, then there are parameters like substrate. So how you can make a microstrip line? First, we will purchase a material. That material will have dielectric constant, which we call epsilon r, and there will be a finite thickness of the substrate. So two parameters are defined for the substrate, which is epsilon r and h. Based on these two parameters, we can calculate what is the value of Z and what should be the width of that strip of 50 ohm line. So it is very simple. When we see the CST microwave studio, then you can just directly put the impedance value and you can get this H and epsilon r, or vice versa. So the characteristic impedance is varying with the epsilon effective. So when there is a epsilon r or epsilon effective, then we have different characteristic impedance. So it varies with the frequency. So this is the problem in the microstrip line. But this variation is very, very less. Sometimes we may ignore this variation. Okay. Now the microstrip line we have, okay, which we made it from a coaxial cable. Now there are components, lumped components we have studied maybe in the network theory, where we have RLC components. The same components we can make by using a small piece of transmission line. If we take a small piece of microstrip line we can make either inductor or capacitor. So how we can make inductor? If you take, suppose this is the width of 50 ohm line, if you take a small width of that line and this length is less than lambda by 4, then this line can be act as an inductor. So this width is less means impedance is high. So in case of inductor, we require high impedance. So if we change the width or we take a very small width of this line, 50 ohm line, then we can make inductor. So how it looks like? This is the series inductor we can make by taking a small piece of transmission line, which should be less than lambda by 4, but thickness should be very low. So the question is here that why we don't use lumped L and C components, which we use earlier like this L and C that we have used in network theory. Here we are using these kind of lines. So the problem of these components, suppose you have this inductor. Okay. So in this inductor, what will happen at high frequencies? Your signal is going from here to here, means with the turn. Okay, so there is a turn in the inductor, signal is traveling in this, current is flowing. What happens at high frequency? This signal jump from one turn to another turn. Why it is happening? Because you are increasing the frequency. So in between two conductor, capacitance may be generated. So in between two conductor, if there is a air, you may get capacitor. So at high frequency, signal may jump from one turn to another turn so that you may get capacitor. So if you are using this inductor at high frequency, it may not work as inductor. It may act as a capacitor. So these components we discarded at high frequency. We use small sections of piece of a transmission line. So these CP is actually the parasitic values because you have this length, okay, and finite thickness. You will connect this line to the 50 ohm line. So because of the 50 ohm line, you will get some capacitance value. So the CP value is very less, but still it will not be zero. Okay. So by using a very small this formula, you can get what is the length you should take and what is the width of this line so that you can make an inductor. So a short section of high impedance line behaves as an inductor. So we can create an inductor by taking a small piece of transmission. Similarly, if we want to make capacitor, if we increase the width of the microstrip line, then we will be able to get the capacitor. Again, the length should be less than lambda by 4. Why we are saying this less than lambda by 4? You can just understand by just taking short circuit and open circuit of a transmission line, which is the general procedure how people follow. So in this case, this shunt capacitor we will make. Now the question is why we are getting shunt capacitor. In the last slide we have discussed it was series inductor. Okay. Now it should be shunt capacitor or series capacitor. Okay. So the microstrip line, we see that top side metal, okay, this is the top side, and bottom side we know that there is a ground. So in between there is a dielectric. So both metal will give you a capacitor value which will be shunt. The signal which will go from top to bottom. Okay. So electric field lines will be from top to bottom. So this component will be a shunt component, not the series component. Okay. If we want to create a series capacitor, then we can take a two transmission line with a small gap. So a small gap will give you a series capacitor. So this is how we get capacitor or inductor by taking a small piece of line. Similarly, not only this inductor and capacitor, you may get shunt inductor or shunt capacitor by just seeing the how we are getting this. Okay. By taking a small width of line or large width of line, we can get inductor and capacitor. Also, we can get some resonators. Resonators like LC. Okay. So this is shunt values L and C. This is series and this is shunt. So both we can achieve by using some changing the thickness of the microstrip line. So this is the usefulness of microstrip line, that we don't need to use lumped components. We can take small sections of transmission line. By just changing the width, we can change the property of that. Okay. So if you want to make a resonators for, let's say, a microwave integrated circuit, then you can create very easily L and C. See this portion, if you create a slot, this side metal, it will give you an interdigital capacitor. Similarly, if you take this small thickness line, it will give you inductor. So LC network you may get. Similarly, shunt parallel resonant circuit, you can connect this line here at this conductor, another port is connected to the another conductor. So here in this case, you will get parallel resonant circuit. So these circuits are planar. Now we move to the other component. We have now created L and C. Now it will be simple to get low pass filter, high pass filter, or maybe band pass, band stop filters. So how we can make? Let's say this circuit, inductor, one capacitor, another capacitor. So what is this circuit? This is low pass filter, 3-element low pass filter. So this capacitor will give you this, you can get from this microstrip line of that piece, okay, L1 length, which will be less than lambda by 4. This inductor you may get by just reducing the width of the line. Again, you have to increase the width of the line, so you will get C. So this transmission line, this circuit will act as an inductor. So this lumped inductor, which we have studied in network theory, now at high frequency, this inductor will behave like say. So low pass filter, maybe multiple elements you may take to get a sharp roll off. So you can increase the number of elements. Similarly, you can take these more number of thick and thin lines. So we call this filter is high-low line filter. High-low is based on the impedance. High impedance, less width, low impedance, high width. Okay. Similarly, you can create very easily high pass filter. Okay. So high pass filter, it is again a low pass filter, but you may create a high pass. In that case, series, what is the series component? C, and shunt component will be L. So you can get this shunt inductor and series capacitor. So by creating a small gap in the transmission line, you may get the series C, and for L, you may take a thin line, but you have to short it to the ground. Then you may get this inductor. Okay. Now we talk about the band pass filter. Similarly, as like low pass filter and high pass filter, again we can create high-low line, and we can get band pass filter and band stop filter by series LC and shunt LC. In band stop filter, shunt LC and series LC, which we have discussed in the previous slides. So like this, you can get series LC, shunt LC. Okay. But there is another way of making band pass filter is taking a different transmission line, different microstrips, just giving small space in between the lines. So this is the structure. It will give you the band pass filter. So by changing the width of these lines or spacing between the lines, we can control the bend of the filter. Okay, if you make it closer, then your bend will be sharper. Roll off will be sharper, but it will be a narrow bend. So if you take multiple sections, you can take just 2 lines and you can create a band pass filter, but it will be a poor band pass filter. Sharp, it will not be a sharp roll off. So if we make multiple sections, we can increase the bandwidth of that filter. So we can get more bandwidth for the band pass filter. So there is a proper formulas to design of such kind of filters, but it is very easy to design. Now we move to the couplers and the power dividers. So first thing is what are the couplers and why we use couplers and dividers. So let's take an example of what we can say that beam steering. In the 5G and 6G technologies, what we have in the future is the switching the beam or steering the beam. So how we can steer the beam? We have to make some beam forming networks. So beam forming networks, you can make by using power combiners or power dividers that we will discuss. So couplers and dividers. So this is the typical example. We have 4-port coupler or 4-port divider. So here let's say this is first port. We are transmitting one signal. It will go towards port number 2 and port number 3. So some power will go from here to here. Some power will go from 1 to 3. And 4 will be the isolated port. So no power will leak from P1 to P4. So we can design such kind of couplers and dividers. So these are some parameters which we define. When we say coupler, then we have to tell the performance. In what basis we are saying that it is a good coupler or bad coupler. So first thing is the coupler means coupling coefficient. How much power you want to couple. So it gives you the 3 to 1. This is the through port. So it is the power transmitted. This is the power which is being coupled from 1 to 3. So 1 to 3 is the coupled power. So you can very easily take a ratio of that and take log of that. Similarly, return loss is the important parameter. It tells if we are giving power to port 1, how much power is reflected back. So if this port is matched with the source, then whole power it will accept. Then this power will be divided in these 2 ports. So that parameter, reflection coefficient or return loss, is more or less same. So when we say return loss, then we will take positive value, and if we say reflection coefficient, we will take minus value. Both are same. Isolation and directivity. What is the isolation of this? So isolation means we don't want any power here because we are using as a coupler. We want 1 to 3, and this is the transmitted power. So we don't want any power which is coming at port number 4. So isolation should be very, very high for this filter. Then it would be a good filter or good coupler. Directivity is the P4 by P3. Okay, so it is the P4 by P3. How much power is coupled and how much power is coming at port number 4. Ideally, we say that power will not go at port number 4, it will be 0, but practically there will be some power. So there should be a ratio P3 over P4. It should be 30 dB or 40 dB. Then we say that directivity of that coupler is higher. So these are some examples of couplers and dividers. So first example we will discuss here, branch line coupler. Okay. So branch line coupler is very simple. All these lines are 50 ohm microstrip lines. So let's say this is 50 ohm microstrip line. Okay. Here at the port side, there is another line, another stub, it is connected. So this is like structure. So this length is lambda by 4. So why we take this lambda by 4 length? You can go for how we design branch line couplers. So there is a proper theory. We will not go in deep to this branch line coupler theory because it will take more time. So 2 stub means 1 stub here, another stub here. Okay. So you can increase the stub means you are increasing the sections. So whenever we want to increase the bandwidth of any component, we have to take multiple sections. In that way, we can make a broadband couplers. Similarly, branch line coupler, there is a rat race coupler. So there is a various application of this rat race coupler. Where we use this rat race, we will see in the next slide. There is another coupler which is parallel coupled coupler. So you have to take 2 microstrip lines closely spaced. Then some power, if you are supplying in this line, some power will be coupled to this. So it is a like directional coupler which we have seen in the waveguide technology. Okay. So same technology now converted into planar, but the concept is same. So this branch line coupler, all these lengths are lambda by 4. This length is lambda by 4. This length is lambda by 4. So what is happening? This width and this width in this picture, it looks same, but it is different. So as you go in the equations, how we can get the width of this line, the impedance of this line is low. So from formula, this impedance becomes low. Because of the low impedance, you have to increase the thickness of this line. So this line thickness is more. Okay, and this thickness is is 50 ohm. Okay, so let's say this is a case that bandwidth we can get from branch line coupler, it will be around 10% if we are using two stubs. If we are increasing one stub, then we can get up to 25%. If you want more, then you can increase the number of stubs. The coupling value is 0 to 9 dB. So we can get a coupling value of 0 in between 0 to 9 dB from branch line coupler. We can, if we want to make a coupler of 12 dB coupling coefficient, then we cannot make it. So why we cannot make more than 9 dB of coupling coefficient? So when you increase the coupling coefficient, the width of these stubs will be changing. So this will increase and this will reduce. So this width, when we reduce it to get more and more coupling value, then it will not be realizable at some point. So it will not be practically feasible to realize this thin line, so that you have to compromise with the coupling value. So you cannot make more than 10 dB coupler from branch line technology. So what are the applications of this? Directional couplers, phase shifters, antenna feed network. We can feed an antenna. Just after putting one antenna, we can feed one side to this one edge, another side to the another edge. So we can make circularly polarized antenna very easily by using this branch line coupler, because the output ports will have more or less equal amplitude. Suppose this is 3 dB coupler. 3 dB means half power is divided. So from here we are supplying a power. This power will go in these lines. Half power will be going at port number 2. Half power will be going at port number 3. So half power means 3 dB. So this power level is equal in both ports, but there is a phase difference of 90° in between the output ports. So how this 90° phase difference comes? So you see signal which is traveling from here, it is directly coming at port 2. So it is traveling lambda by 4 distance. But how the signal is coming at port number 3? Either it is traveling from here to here, or it is traveling here to here. So another lambda by 4 distance, this signal will travel. So another 90° phase shift will be generated. So at the output of this branch line coupler, there will be a 90° phase shift, but amplitude will be same. So we can use to feed the antenna, which we know that if antenna will have two feed with having 90° phase, we can get circularly polarized antenna, which will be useful, and it will be discussed tomorrow. Okay, so we will go to the next slide. Two-step branch line coupler. There are some, I put some values to get some understanding. If we have a 3 dB coupler, then this value of impedance is 35 and this impedance value is 50. So based on the impedance value, we can get thickness. Now, if you want to increase the 6 dB coupler, then this ZOA is increasing and ZOB is reducing. So when we get 10 dB coupler, we will get 150 ohm, and 150 ohm means it should be very, very thin. So very, very thin line we cannot realize by using standard photolithography process. Either you may use a very sophisticated technique, then you may achieve a 10 dB coupler. This is just one graph to understand that how power is divided in the output ports. So this is the S parameter. Okay. So why we measure S parameter at high frequency? Why we are not measuring Z and Y parameter, which we measured at low frequency, maybe at network theory. So in the network theory, the source which we have taken, it was around 50 hertz or 60 hertz. Here the signal frequency is very, very high. So when signal frequency is very, very high, then you cannot measure voltage and current by using voltmeter or maybe multimeter. So this voltage and current you cannot measure uniquely. So this Z and Y parameter we cannot define for high frequency circuits. We have to go for some parameters. Those are related to incident wave, reflected wave, and transmitted wave. So here 4 parameters. S11 is the reflection coefficient, which is the red curve. If this red curve is going below minus 10 dB, means it is acceptable value and your circuit is accepting power. So 10 dB means 10% power is reflected back from that port, and it is the acceptable value given by the FCC. Some standards are there where we can go up to minus 10 dB. Okay, it is below minus 10 dB, then it is better. Now you see the coupling. S21 and S31 are the coupling coefficient because we are measuring at port 2 and port 3. So port 2 and port 3, if you see from here to here, this this blue line and this, what is this color? Some brinjal color or whatever. So it is matching in this frequency range. So S21 and S31 are equal in this frequency. So we will define bandwidth of this coupler based on the coupling values, not from the S11 parameter. Normally we define the bandwidth of a component by seeing the S11 component. But for coupler or power dividers, we have to define the bandwidth where we have equal S21 and S31 value. So this is little bit different from definition point of view, the components. Now we see one or two application of branch line coupler, which is very interesting. So duplexer. Okay. So when we have to make a duplexer, then we can use BLC branch line coupler to make a duplexer. So why? What is the use of duplexer? Suppose we have radar. We want to transmit a signal, and this radar will again receive that signal. So here duplexer, we can transmit that signal. That time the signal will not reach to the receiver, but this signal is coming from the other directions. Then this signal will go towards the receiver. So this is the function of duplexer. It will switch in the transmission mode so that this transmitted signal will go directly to the environment. So how we can make this by using BLC? Suppose you have this 3 dB branch line coupler. You have two output ports. You can directly connect two pin diodes. So these pin diodes is connected at the output port of the branch line coupler. And you are taking another same branch line coupler and you are terminating one port with the 50 ohm impedance so that all power will be absorbed and make it ground. Here you have connected one receiver. Okay, so let's see how it works. So this is the transmitter. This side it is the receiver and this side is the antenna. Okay, so in the transmission time, what will happen? When we will transmit that signal, what we will do, we will switch on the pin diodes. If pin diodes are switched on, then it is connected to the ground. So both pin diodes will be connected to the ground. So it means when signal is coming towards this diode, it will found that it is grounded. So signal will be reflected back. So both signals will be reflected back and these signals will go towards this antenna and it will be combined here. So at this transmitter signal will go towards the antenna. No signal will pass from here to here because there is a ground. Okay. Now in the case of reception, what will happen? If it is open, let's say this is open, okay, then this signal will go directly from here to here. Okay, so when signal is coming from antenna, so this signal will come from here in this direction and in this direction. Okay, so this signal will go from here to here, here to here. These diodes are off. Okay, so this signal will go here and here. So you will receive signal at the receiver side. So this is the simple example of branch line coupler and we are using to make a duplexer. So this is one example of a parallel coupled coupler. So parallel coupled means two microstrip lines. Okay, you are making two microstrip lines and there is a small gap between the lines. So whenever you feed any port, this signal will couple to this port. So normally these coupled parallel coupled couplers are used to verify how much power is going in the main line. So you can connect a very small or what we can say 40 dB or 30 dB coupler. So you can sense the power because in the high power lines, you cannot directly connect the receiver at the output side. So to check how much power is going in the main line, you can extract some power from that main line, and you can calculate very easily how much power is going in the main line. So this is the benefit of these couplers. So these parallel coupled coupler or branch line coupler, if you see the difference, okay. So advantage of parallel coupled coupler, it offers large bandwidth, single section will give you 40%. Input ports perfectly match at all the frequencies, loose as well as tight coupling possible. So if you want loose coupling, if you want tight coupling, means if you want 10 dB coupling, if you want 40 dB coupling, you can achieve from parallel coupled coupling. But the same coupling you cannot achieve from the branch line coupler, because we also we see in the previous slide that if you go beyond 10 dB coupling, then you cannot get it, because this line will be very, very thin. Rat race coupler is actually very, very useful component in case of this RF circuits nowadays. So whenever we want to track any target, so what we do, we send one signal from radar, and this signal will be reflected back from the target, and again we receive that signal. So we receive that signal by using some antennas. After the antennas, we will use this device, rat race coupler. Okay, so rat race coupler, if I go directly to this next slide, if there is a feed input to port 1 and port 3, let's say we feed signal at port 1 and port 3, then what will happen? Different signal available at port 4, which is the difference port. Some signal will available at port number 2. So if we receive signals at port 1 and 2, these two signals will be added at port number 2 and differ by port number 4, subtracted at port number 4. So this is the speciality of this rat race. It is because of the different length. So the port is connected, one port is connected and another port is connected with a distance of lambda by 4. Here again lambda by 4, here again lambda by 4, but this distance is 3 lambda by 4. So what is happening here? If you send this signal at port number 3, this signal will go from here to here. Similarly, one signal will coming from this port and it will go here. Okay, so both signals reaching at port number 2 will face same phase. This signal will travel lambda by 4, this signal will travel lambda by 4. So this signal will have same phase, so it will add. What is happening at port number 4? This signal will again go in this side also. This signal will go in this side also. So this is facing only lambda by 4. This is facing 3 lambda by 4. So there is a difference of 180-degree phase shift. And we know that if there is a 180-degree phase, then signal will be cancelled out. So we are getting this subtraction of signal at port number 4. So in the at the reception side, we use this rat race device. So application of the rat race in balanced mixers, monopulse comparators, and phase shifters. So we will discuss phase shifter, then we will see how we can do that. But the two components, two application, balanced mixer and monopulse comparator, are the useful application of the rat race. And these are actually practically in use. Now we come to the power divider. Okay. So after coupler, now we want to discuss the power divider. So for power divider, what we require? We require at least 2 output ports, 1 input port and 2 output ports. So 3 ports should be minimum for a power divider. Power divider is, you can just connect a microstrip line here, another 50 ohm microstrip line here, another line is here. So power will coming from 1, it will equally divided to port number 2 and 3. Okay. So it looks simple, but it is not that simple. Okay. This power will not go into this half power and half power. Similarly, if you combine power, let's say you are receiving signal at port number 3 and you are receiving one signal at port number 2, it should be combined at port number 1. But it doesn't happen in this case of power divider. What will happen? This signal which will coming at port number 3, it will also go to port number 2, which we don't want. So this basic power divider doesn't work at any frequency. Okay. So there is an advancement of this power divider is Wilkinson power divider. Okay. So Wilkinson power divider looks like this. So 150 ohm line initial at the port side you have connected. Then this line is a different impedance and length is lambda by 4. So this is root 2 Z naught, means 70 ohm impedance line. You can calculate very easily by using formulas. So this 70 ohm line, again it is 70 ohm line, and we are connecting one resistor in between the output ports. What is the role of this resistor? Okay. When we transmit one signal, it will equally divided. It is okay when we are using this component as power divider. But the same component, if we want to use as a power combiner, then there was an issue that when the signal is coming at port number 3, it should not go at port number 2. So there is some signal which is traveling from port number 3 to 2, it will be absorbed in this resistor. And this resistor value is around 100 ohm. So this is you will understand very well that when you see this design equations. So this power divider is actually practically in practical use. So this power divider will have more multi-function, or what we can say multi-section power dividers. So this is actually Wilkinson power dividers, which we use at microwave frequencies. The last component is we want to discuss is phase shifter. So what is the use of phase shifter? We want to give some phase, right? So where we want to give some phase, suppose this we can take an application of this communication where we have this 5G. So we want to steer the beam, then we need phase shift to the different elements. Okay, so in that way it may be analog or it may be digital. So this is the case. We have multiple antennas. Different phases are there. You can feed some phases, okay, and you can change these phases so that you can change the direction of main beam. So this is the radiation. Let's say this radiation is coming in this direction, and you want to steer this beam at some particular angle. Then you can calculate this angle based on the calculation of phase. So if you give different phases to different elements, then you can steer the beam either in this direction or maybe in this direction. So these phase shifters we have to make connected with the antenna port. So how we can make these phase shifters? One very simple example of phase shifter is by using pin diode. So when we are using pin diode, then we may have two types of phase shifter. One is reflection type, another is the transmission type. Okay, so we will take one example here. Okay. This is the circulator coupled phase shifter. So this is the circulator, or we know very well that if we feed from here, it will go here. If you feed from here, it will go here. If you feed from here, it will go. So like in one way it works. Okay. So when you are feeding this signal 1, it is coming at port number 2. And if you are feeding from port number 2, it will coming at this port. So what is happening by using pin diode? Let's say this pin diode is off. Off means this ground is not connected. Okay. So when this ground is not connected, signal will go up to this point and then signal will be reflected back. In one case, if you switch on this diode, then signal will be reflected back from this portion only. It will not travel this length. So one time it is traveling like this, another time it will be reflected back. So extra 2 delta L, it will be travel when this diode is off. So 2 delta L, we say difference in the path. So we can calculate the phase difference. So phase difference we can calculate by using path difference by using a simple formula 2 pi over lambda into path difference. So 2 delta L path difference will be there. So you can get a different phase from this small component. Okay, one more component I want to discuss here is this. Okay, switched line. So what is switch line? It is just very simple. You can take a 50 ohm line here, then you can connect another line and you can connect here another line. Okay, so these line will be connected through some switches. So when you have this switch, if you switch on it, this line will be connected. If you switch on it, this line will be connected. So this will be the path. So when this D2 are on, then that case D1 will be off. So there is no signal will go in this. So all signal will go in this line. So this line length is different. When in one case, if D1 is on, D2 is off, then this line will be connected. So this length is different. So you have two different length, you can create two different phases. Okay. So J51 and J52 you can create very easily by using these four pin diodes. Why we use always pin diodes? Because the PN diode we cannot use because of the low switching speed. Pin diode will have very high switching speed. So we use pin diodes in case of switching at a high frequency. Okay. So the next, most of the components, if you see in the RF domain, any circuit, if you see transceiver, then you will have all these passive components: couplers, power dividers, filters, and the parallel coupled couplers and the phase shifters. Okay. Rest are the active components which we are not discussing here: power amplifiers, oscillators, mixers, or maybe PLLs. So this just I'll give you a flavor of antenna which is just a planar. So this planar antenna, it similarly it looks like a microstrip line. Okay, we cannot distinguish a microstrip patch antenna from a microstrip line because structure is more or less same. Backside metal, top side some again metal, and in between there is a dielectric. So same thing happened in the case of microstrip line, where this is thin line, this is microstrip line. It is connected to a large thickness metal. Okay, so this dimension of this metal is different from the microstrip line, and this we are calling patch. So why we are calling this patch? Because the microstrip line with this thickness, with this width, it is not radiating. But if you increase the dimension of this line, then it starts radiating and it became radiating patch. So the concept, if you see the cross section of microstrip patch and microstrip line, it will be same. Top side metal, bottom side metal, and in between dielectric. But the property of the line and patch is quite different, and it comes from the dimension. If microstrip line, if you increase this dimension and this dimension becomes lambda by 2, then it starts radiating. We know that any antenna, if it is having length lambda by 2, then it starts radiating. Okay. So this part, the basically this planar antenna, we will discuss maybe tomorrow because we cannot cover that part. So I will show you some part in the CST tool that how we do all these designing. So I'll open one CST Studio Shoot. It is actually freely available. I also downloaded the same from that website, CS2 Studio Shoot 2024. We will share the link so that you can also install in the your computer. It is very simple. So it is learning edition. Now this is the window. This is the main window of CST Microwave Studio. So how to open it? You can just create a new template. It is very simple. And there are various options in the CST Studio. You cannot only design microwave and RF components. You can design components at very high frequency, starting from very low frequency. If you want to get some EMI EMC thing also, you can do in the softwares. So here we are discussing the RF and microwave domain. So we will select this. So when we select it, again, you have some antennas, circuit components, some radar applications, biomedical, which is SAR. Suppose you want to design an antenna for mobile, then you have to check SAR value, which is specific absorption rate. Then we have periodic structures like metamaterials. We have optical applications. So all these applications, this CST may be useful. So what type of component or the circuit you are making, you can select any of the tile from here. So we are going to circuit and component. So I'll choose here. Again, you can choose it is waveguide type or planar type or maybe some other type. So we are choosing here planar, let's say planar filter. Again, there are some calculation tools. So this software doesn't do anything. Okay. So we have to tell this tool to do some simulation. Okay. So for simulation, for calculating the E and H field values, we have to choose the solver. So there are two types of solvers in the and this CST studio. One is the time domain and another is the frequency domain. Okay. So what is the difference in time domain and frequency domain? It is not that simple to see. Okay. If we are suppose designing a microstrip line or maybe filter or power divider, you cannot find any difference in frequency domain and time domain. It is actually when you have complex structures. Okay. When you have a broadband structures, then it may be faster in time domain, it may be slower in frequency domain. Okay. So that is a separate story. By default, we can set the units, it is in millimeter and frequency is gigahertz. Okay. So when here you can select the frequency. Suppose you want to check a performance of a component from 1 to 10 gigahertz. So you can set here minimum frequency 1, maximum frequency 10 gigahertz. Okay. So now it is ready. So when we click finish, then you have this window where we can design circuits. Okay. So this part we have to design a 3D model. Then results you can see in this side. Okay. So we'll take a very small example of microstrip line, which is very simple to design. Okay. Also, I will share one or two link for YouTube video so that you can see there is a CST tool and people are designing some components. You can watch those videos very easily, you can understand. Okay. So I will not waste the time to design the circuit. Okay. I'll already simulated some components, so I will show you those components. Okay, so this is the transmission line which we discussed. So this is the microstrip line. So in this, if you see backside, this is copper. Okay. So whenever we purchase any substrate, any dielectric material, there will be a copper material and both sides. Okay, so one side here it is copper, another side this is small strip. Again, it is a copper, so you can assign this copper value as well. We assigned PEC, which is perfect electric conductor. So you can choose any metal in the software. Okay, it doesn't affect too much in the performance. So this microstrip line is a 50 ohm line. Why I am saying this 50 ohm line? Because the width of this line gives us the 50 ohm impedance. So how we can calculate? So if you see, there is a calculator in this CST tool. You may get somewhere a tool where you can calculate very easily this impedance value from the width. Okay, so you can check maybe in this tool that where is the calculator. I think in home there is a calculator like this. So in this calculator you may get very easily the values of the 50 ohm line. So this 50 ohm line you can create, and now you have to assign the ports. In hardware, we solder SMA connectors at both the ports. So this SMA connector, we don't need to make in the software. We can assign a waveguide port. So waveguide port will act similarly as coaxial connectors. So one port at this side, another port at this side. Okay. So it is that simple. It is 3D model. There is some thickness of this PCB. It is 0.762 mm. 0.762 mm is 30 mil substrate. So whenever we buy substrate, it comes not in the mm dimension, it comes in mils. 10 mil, 20 mil, 30 mil. So these are the standards. So when you convert these mils in mm, then 30 mil we will get 0.6762 mm. You cannot choose any random value for this because this substrate you cannot make. You have to purchase it. So you first see what is the thicknesses available for that substrate. Okay. So this we choose here, Rogers 5880 substrate, which is a dielectric constant of 2.2, which is a very high quality substrates. For commercial application, people don't use Rogers substrate because it is very costly. People use FR4 substrate, which is very, very low cost substrate. There are difference in the performance in the circuit, but who cares about that? Because it is commercial purpose used, and people go for low cost circuits. So now if you see the results, so in the left side, all the results we can see. So first results, let's say it is S parameter. So in S parameter, you can see S11, S21, S12, and S22. Because we have two ports, we will have four parameters. So what is the value of S11? You see, this is the S11. S11 means reflection coefficient. So reflection coefficient below minus 10 dB is quite acceptable. So this value is below minus 25 dB. It means reflection is very, very less. S21 is the transmission coefficient. So whatever power you are giving from port number 1, it should reach up to port number 2. So this is the value of S21. So S21 is 0 means it is in dB. So if you calculate the value, then S21 will be 1. So if you take a log of 1, it will be 0. So if it is near 0, then it is ideal substrate, but we have to take because we know that there is nothing ideal in the substrate. We have to purchase this substrate. It will have some finite dielectric value, or resistivity will be there for the conductor also, because copper will not be a pure conductor. Okay, so in that case some loss will be there. So it may be 0.2 dB, 0.3 dB, or maybe more. FR4 it may have 0.8 or 0.85 dB. So this is the loss, and with respect to frequency this loss increases. So when we see or draw these graph, then this loss will increase at frequencies. As you go at high frequency, losses will be more. Now, this is the S parameter. So S parameter tells how much power is reflected back, how much power is going from port number 1 to port number 2. Also, we can check what are the field lines. So field lines you can check in the 2D results. So field lines are E field and H field. So if you check E field, then we know that this arrow will go from top to bottom. Okay, so you can check this field lines is correct or not. Also, you can check the mode. What is the mode propagating in the microstrip line? Okay. So all thing we can do. Surface currents. Surface current also we can check. What is the surface current? In if you see in we will discuss this surface current in tomorrow lecture, where we will see the antenna, because antenna can be understood by seeing the surface currents. If it is circular or if it is linear, by seeing the surface current value we can check how much power, how this surface current is flowing. Then we can see by animating this field, so how this power is moving from port number 1 to port number 2 with respect to these fields. So E and H are varying continuously with time, but every time it will have the power direction in the along the x-axis. So power is flowing from here to here by having some field configuration of E and H. So this is the case of a transmission line. Let's see one more component, which is a branch line coupler. Okay, so this is the branch line coupler, which we have discussed in the theory. You can make very easily. These lines are more thick line, means width is more, and this width is similar to the 50 ohm line. So it is 3 dB coupler. 3 dB means half power will be delivered to this port and this port. How we can check? We can check the results as parameter. This filter, this is designed at around 3.3 gigahertz. So you can check S11. Let's say first this S11. So reflection coefficient is well below minus 15 or minus 20 dB. What is S21? S21 is this and S31 is this. So S21 and S31 are matching at this portion. So this is the only bandwidth we are getting in this branch line coupler. Also, if you see one more result, which is S41. So this is the isolation port which we discussed. So isolation port is again having very less value. So in the S41 we are not getting any value. Okay. So we are not getting power at port number 4. So it is isolated. Another component, we see that power divider that we discussed. Okay. So this is Wilkinson power divider. Okay. So Wilkinson power divider is, we discussed that it is 50 ohm line. Then it is 70 ohm line. 70 ohm means less thickness compared to microstrip line. So it is 70 and lambda by 4 is the distance from here to here. Then there is a resistor we connected here. It is 100 ohm lump resistor. You can check the value of resistance. It is 100 ohm. So in this way, we can design these circuits very easily in the software, and all these links I will share that you can maybe do hands-on in the CST studio, because we don't have sufficient time to cover that part. Based on the theory which we discussed, based on that we can design easily these components, and we can see the simulation. Then we can go for fabrication and compare the simulated and measured results. So I will I think time is already over, so I'll take a few questions if people have.
Participants, if any questions, you can actually write within the chat box, or you can unmute yourself and you can ask.
Good evening, sir.
Hi, good evening.
With respect to the particularly filters, I have one question that
Yeah.
what
Yes.
is the possibility to have meta materials in case of filters?
Actually, sir, if you want to go for filter, then you cannot use metamaterial. Metamaterial is actually helping or improving the performance of a microstrip based circuit or maybe other circuit. It is the extra part. It is not the basic thing. So when you want to improve something with that filter, you can use some metamaterial or maybe some more unit cells so that you can improve some part. Maybe reflections, if you want to reduce, then you can use metamaterials along with that filter. But
Okay,
solely metamaterials will not work.
means for a specific purpose, we can deploy a filter on it.
Yes. For a specific purpose, yes, we can do. Normally in antennas, if you use this metamaterial, normally we use metamaterial for some specific band, and we can use that metamaterial as a filter, either band pass filter or it may be as a band stop filter.
Yeah. Thank you, sir.
Thank you.
So there is one question on chat box.
Ah.
Can we measure specific absorption rate of antenna?
Of antenna. Actually,
Yeah.
absorption rate of the antenna, if this question is related to SAR value, then we can discuss this part tomorrow. Then it will be simple, because SAR value we didn't discuss how we calculate the SAR value. If your antenna is uh, having ground plane on the back side, then the SAR value will be less. Okay, but it doesn't happen in case of mobile, because backside of the mobile, if you see, the printed antennas is there. So you have to calculate the value of SAR, which is actually high. So when this RF is, we are taking that RF and we are talking some people by putting this phone near the ear, then if you continuously talk, then we feel some sensation, heat sensation. So this RF is actually disturbing the tissue layers. It depends. So this parameter actually tells that how much power can be transmitted from the mobile. So there are actually limitations. So there is a guidelines given by FCC, Federal Communication, so that we cannot transmit more than that power. So this mobile value, if you see in your mobile, if you check SAR value, it will be around minus 105 or maybe lesser value nowadays. So it may not affect us, but if you are getting these EM waves continuously for long hours, then it may affect. SAR
Okay,
value
ma'am.
can be reduced by metamaterial. So metamaterial can be useful in case of reducing SAR value. Yeah.
Thank you, sir. So one more, how
Hmm.
to automatic optimize design for particular frequency in CST?
Okay, actually, not in this version which which we discussed, learning edition, there is no optimizer. But the license version CST, if you have, then you can use optimizer. But normally people don't suggest optimizer because parametric analysis, it is you should have some basic background. Then we can use a optimizer. Otherwise, it will not give anything. It will take more and more time, maybe in months it will give you some result. Optimizer is
Is
there, but there should be some basic idea that how we can put this optimizer. We cannot
you should
take
have
some.
some mathematical result, is it, sir?
Sorry.
Is it that first you should have some kind of results mathematically by calculations
No,
and
no,
then
no, no,
we
no, no. It will
can
not
go
give
on?
you any calculation result. It will give you the S parameters. But if
Uh,
suppose you optimize, means you put some value S11, we want minus 15 dB.
yeah.
So it will continuously simulate with the different parameter value and it will give you minus 15, but it may take more time.
One more question, sir.
Yes.
What precautions we shall take to match the impedance when we use several resonators while designing the filter?
Yeah, actually, this impedance matching is a very difficult task many times because you have multiple elements, then this impedance is change. So every time this input and output impedance matching networks we design for feeding the circuits. So these matching networks are again based on the stubs, shunt stubs and series stubs. So again, we have to check the impedance value. Okay, what will be the maximum value of reflection coefficient?
Of
Okay, reflection coefficient, if you see practically, ideally it should be minus infinite, but practically it will never give you minus infinite value. If it is minus 20, minus 15, and it is acceptable. And in lower side, it may go up below near to zero. It will not never cross the zero in positive side in passive circuits.
There is one more question, Moekar madam. To learn various design concept of microwave technology, can you refer any suitable books?
Okay. DM Posar is the writer for that book. Maybe if I have this book, I can share. Otherwise, I will share the link, title of the book, and author.
Thank you, sir. Any other questions from audience participant? Yes. Yes. Any questions? So I think book for antenna design concept.
Yes, yes, and I
Uh,
also I will. Some people are asking PPT. Yeah, I will share the PPT to ma'am. Then ma'am will share.
yeah, yeah. Once PPT is shared with by
Yeah,
sir,
yeah,
we'll
sure.
definitely post to them.
Surely
Yes.
I will
Sure.
share.
Sure, sir. Any questions from participant side?
A wonderful session, sir.
Thank you, ma'am.
Yeah, it was really wonderful experience.
Yes, sir. It's really a good session. So, okay, sir, one more question, I think. How
Yeah.
to know the physics behind antenna design?
Okay, so antenna we will cover tomorrow. So we will discuss that part surely.
I,
Participant tomorrow also there is a session of Dr. Rajesh Singh sir. So remaining part he will be explaining in tomorrow's session at the same time,
And
6 to
ma'am,
7.
maybe you may request participant to join little early so that we can
Yes,
start
yes,
from means with time 6.
yes, yes.
And
Participants
yeah,
please
so we,
join so that we can cover more topics
yeah,
and
yes, yes, yes,
we can take the benefit
yeah.
of the expertise, right? So tomorrow, please join early. Today we started very late, like 10 to 12 minutes. So please join tomorrow on time.
Yeah, it would be better.
Yeah. Any
I
specific
request you.
material available? Please give, sir. Some questions are there.
Okay, person, if you are near to Pune and Mumbai, then you come to DIAT, then we can definitely give you some materials. We have Rogers, we have FR4. Even in DIAT, you may come for some measurements and fabrication. It is also available. So it is not means restricted.
Basically, for antenna design, anechoic chamber is available,
Yeah,
sir.
and upper chamber, most all of the facilities are available,
Yeah.
and everyone is welcome to come to DIAT. We are helping people to do all the measurements.
Uh,
So, yes,
I
good
request,
evening, all.
yeah, just a minute, ma'am. I just
Yeah.
request all the participants to switch on their camera so that we can have a pic.
Yeah.
Sir, can you stop your sharing?
Yeah, sure.
Please switch on your cameras. Yes, it's done.
Okay, thank you. Thank you very much. Okay, then, yeah, you have another session, so you please continue. I'll take a leave.
Rajeshwari madam, you are muted. Rajeshwari madam, you are muted. Unmute yourself.
Okay, sorry.
Mhm.
Thank you very much, Rajesh Singh sir. On behalf of organizing committee and participant and Department of Electronics and Telecommunication Engineering, I would like to express our deepest appreciation. And of course, we took forward to staying connected and hope that we will have a privilege to hearing you again one more time tomorrow. And once again, thank you very much,
Yeah,
sir.
thank you very much. It is my pleasure that you have given opportunity, and I love to see more than 100 people on the FTP. So it is actually good interaction, more interaction.
So your session is really wonderful. Thank you very much. We actually gain a much knowledge in that actually. So we have a lot many questions. I request participant to write all questions tomorrow and
Yes. Maybe they may
yes,
email me also. I can
yes.
reply, no problem.
And please join dot 6 o'clock. Maybe before 6 also you can join.
Yes. Before 6 is also okay for me.
Yes. So thank you very much, sir, once again.
Thank you, ma'am. Thank you.
So we
Okay.
have one more session.
Yeah. Please continue. So I'll.
Yes, sir. Thank you very much. Deepali, madam.
Yes, welcome Dr. Amit Kumar Khade sir. I think sir had joined.
Yes. Hello everyone.
Yes, good evening sir.
Good evening.
Yeah, Dipali madam will be introducing. Madam.
Yes, ma'am. Good evening, everyone. It is my pleasure to introduce our esteemed resource person for today's session, Dr. Amit Kumar Khade, sir. Dr. Khade completed his PhD in VLSI domain from the renowned College of Engineering, Pune. He is a hands-on expert in Cadence, a leading tool in the field of electronic design automation. With the 15 years of teaching experience at Cummins College of Engineering, Dr. Khadi has guided and mentored numerous students, leaving a lasting impact on their academic and professional journeys. His research work has been widely published in the reputed journals, including Elsewhere and Springer, reflecting his dedication to advancing knowledge in his field. Currently, Sir is applying his expertise in the industries as a functional safety manager at Lear Corporation. With his strong foundation in academics and valuable industry experience, Dr. Khade sir is uniquely positioned to share insights that bridge theory and practical as well. We are fortunate to have him with us today to enrich our discussion. our learning and understanding. Please join me in welcoming Dr. Amit Khade, sir. Over to you, sir.
Thank you, ma'am, for such a wonderful introduction.
Yes, sir.
Am I audible?
Yeah,
Yes,
yeah,
sir.
it's
You're
all
audible.
you. Clear
Yes,
audio.
You're audible, sir. You're audible.
Okay, thank you. Hello. I shared the screen. Are you able to see the presentation?
Yes, your screen is
No,
visible, sir.
but sir, your PPTs are not visible. That Gmail is
But
opened over here.
PPTs are not.
Okay. One minute. So now,
Yes, sir. Now PPTs are visible.
okay. So good evening, everyone, and let's start with our today's presentation. Today, I'm going to elaborate some safety analysis methods which are widely used in most of the product-oriented industries. It may be automotive industry, it may be a VLSI industry, or it may be any industry. And the primary objective of this safety analysis method is to identify the faults which can lead to the product failure. Okay, because the product failure is a huge loss to the company or any organization, because there are a number of things which involves like financial aspect, reputations, then the legal claims and all these things. And that's why when you are developing any product, there are different phases of the product. So at every stage, it is expected that we have to perform the safety analysis. And what basically we are doing as a safety manager, we have to identify the possible faults. Now the faults, it may be a broken of wire, it may be the opening of fuse, or it may be a failure of transistor, or it may be a failure of some ICs. But that fault has a huge impact on the rest of the circuitry, and which creates the failure in the product. Okay, so today I will try to cover some basics of these safety methods which are widely used in all the product oriented industries. Before starting to this presentation, let's have a small or brief introduction about me and my company. Ma'am has already given my introduction, so I will not repeat that. Now, about my company, obviously, I'm working as a functional safety manager at a Lear Corporation, and a Lear Corporation is one of the company which is listed in the Fortune 500 companies list. Now, we have a two divisions in Pune, basically a seating division and a system. Basically, we are in automotive industry. Okay, so first is the seating. So we are manufacturing the car seats and we are providing that seats to the various companies. And second is the electronic system. And basically I'm working in the electronic system. When we are talking about the electronic system, we are having the different division like core electronics, electrification, platforms, lighting, and many more. When we are talking about the electronics product, which are placed in the different cars, now every single car which are running on the road, either in USA, UK, India, or in any territory of world, has at least one of the Lear product inside that car. Okay, so that product may be a onboard charger, the product may be a battery management system, it may be a headlamp control modules, there are circuit breakers, or there may be a what we can say that control modules or body control modules and many more. So we are having main business in product development in the area of car, like ECUs. Basically, we are manufacturing or developing the electronic control units. Also, we are having the another business in wire harnessing, which is mainly deals with the development of high power connectors, which are widely used in the EV cars. Okay, because now the battery voltage is in the range of 400 volt to 500 volt. So we have to build wires or connectors which should sustain with that capability. So this is the agenda of today's presentation. We will start with the functional safety. This is a very popular terminology in any industry. When visit any product development industry, there are three divisions. First one is the engineering division, second one is the quality division, and third one is the functional safety division. So the engineering division mainly responsible for developing the products as per the requirement. Then the functional safety department is responsible to assure that your product is the safety compliance, and the quality department is responsible to assure that the product has maintained the particular checks or maintain the particular quality with the certain checks. Okay. Then we will start with the safety analysis methods. There are various safety analysis methods, but two methods are very popular in all sort of industries. First one is the fault tree analysis method, and second one is the failure mode and effect analysis method, that is the FMEA. But when you are going for the VLSI industry or any industry which are having the hardware, basically electronics hardware like resistor, capacitor, or PCBs, so there a third analysis comes into the picture, that is the failure mode effect and diagnostic analysis, which is the extension of the failure mode and effect analysis. So mainly we will focus on the FTA and FMEA, and if time permits, we will go for the FMEDA. So when we are talking about the safety, so in general, when people are talking about the safety, it is always common question, how you define the safety. So we are saying that, okay, my product should be safe, but what is the meaning of safe? So always remember or keep one thing in mind, when you are procuring any product, it always has certain defects. No industry will develop the product which is completely defect free or fault free. But when I'm purchasing a product, though it has a defect, so that defect should not cause a failure which has undesirable risk. Okay, so in electronics world, so when we are talking about the safety, or in case of electronics product, when we are talking about the safety, basically it is a product which is completely freedom from unacceptable risk. Means risk is always there, but it should be free from the unacceptable risk. Now, when we are talking about the unacceptable risk, so which risk we are treating as an unacceptable risk? So obviously the risk which are causing any type of damage to the health of people. Okay, so these kind of risks are not acceptable in any territory. It may be US, it may be a UK, or it may be Asia. Okay, if the product has a fault which cause a risk of a physical injury to anyone, now when I'm talking about the anyone, it may be a human beings, it may be animal, it may be a surrounding factor, like it may be a buildings or anything. So the product should not cause a damage to any kind of or any kind of physical injury to any sort of living and unliving things. Okay, and then the environment, whatever the product we are using, it should not violate the environment territory rule. Every territory, it may be UK, US, Asia, they have a certain norms related to the pollution, related to the sound, related to the other factor. So our product should not affect or should not cause a risk to these standards. Okay, so if the risk comes under this kind of category, this risk are not acceptable at all. So when I am talking about the safety, so it is expected that the product should have a risk which is unacceptable risk. Okay, or it is a freedom from the unacceptable risk. Now the safety has a different aspect. Means the people may talk about the product safety. Okay, the people may talk about the environmental safety, or the people may talk about the human life safety or infrastructure safety. But when we are talking about the electronic safety, so there is a concept called as a functional safety. So this is the word which is commonly used for the electronic product. Now, when we are talking about the functional safety, so what is the objective of functional safety? Any failure or any fault in electrical or electronic system should not cause an unacceptable risk. If the fault in the component or the failure in the component has an unacceptable risk, it should be detected, addressed, or mitigated by some mechanism. So when we are talking about this kind of safety, this is called as a functional safety. And we have a very standard definition for a functional safety. So functional safety is the part of overall safety of the system. Now, when I'm talking about the system, it may be a huge electronic system like ECU, or it may be a single board or piece of equipment that depends on the safety mechanism. Now, what is the safety mechanism? Let's say now we are an electronics engineer. Okay. Suppose I'm having a memory. It may be a RAM or ROM. We know that what type of fault may occur in a memory. It may get, or one of the location may get stuck to the high supply voltage, or some location may get stuck to the low supply voltage, or there's a flip of bits in the memory location, or the memory location has some garbage value. We can say that it's a corrupted values. So something fault is there in the memory. To detect that fault, we have the error correction methods, ECC methods. Okay, so what is the job of ECC methods? Basically, it scans the memory location and it identifies which location is corrupted. So it is the job of that ECC to identify the memory corruption and to correct it. Okay, that's why these kind of mechanisms are called as a safety mechanism. Okay, so when I'm talking about the functional safety, it is the part of overall safety of the system or piece of equipment that depends on the safety mechanism operating correctly in response to its input or failure in the predictable manner. Now, in the industry, there is always a concept of fail-safe or safe state. Now, what is the meaning of fail-safe? If your product fails, at least it should operate in some degraded mode. Okay, let's have an example of headlamp control module in the cars. So what is expected that headlamp control module shall not be off when you are in a driving mode in a night. But if this happens, we know that our headlamp control module has a different functionality like high beam, low beam, or side indicator. So in that case, if something goes wrong, it is expected that at least minimum low beam shall be on. Okay, so that is called as a fail-safe operation. Means if the problem is with headlamp control module, not all the beam should be in off state. At least low beam should be in a on state. So the driver has some comfort to drive the cars in a night mode. So this kind of failure is called as a failure in a predictable manner or in a fail-safe mode. Now there is a always concept why we need a functional safety. Okay, so it realized that in automotive industry, in earlier days, most of the automotive industries or most of the industries has a mechanical machineries. Okay, there is a very small electrical part, and the large part was the mechanical part. But as the VLSI technology advances, as the software technology advances, it was possible to integrate more and more functionality in a smaller electronics part. And nowadays, most of the mechanical machineries are replaced with the small electronic gadgets. Even if we compare today's electronics world, let's consider it is a TV, let's consider it is a car, it is a mobile. So what we found that in a small gadget, we are having the n number of electronics functionality. Okay. Now, if we are talking about the TV or mobile, so what is expected in TV and mobile? The particular device should not blast. Okay, this is what the expected functionality, safety goal. That's when you are running the operating the TV or mobile, it is expected that there should not be any failure in the electronics component that can cause extreme heat inside the device and cause the damage or blasting of the device. Okay, now same is true with the different things in a different domain. When I'm talking about the different scenarios happens in the different areas. Okay, so here I have listed few scenarios. So it is observed that during 2004 to 2009, there was near about more than 100 accident, which happens only because of the stuck of the accelerator. Okay, so we know that in a car we are having the acceleration system. We accelerate the car, we get the speed. But what happened when you remove the feet from the pedal, but still the acceleration gets stuck? Obviously, you are going to hit the obstacle, and that was the one of the reason of the failure. Means the acceleration system gets failed, and because of that, the people face the accident. Then, this is not the only thing. The people realized that there was a failure in the brake system, which caused near about 30 crashes. Okay, or there are more than 20 injuries. This is related to the cars, but there was some incident in the railway department also. Okay, so the railway department has an electronic brake system, and unfortunately, the electrical or electronic system which were controlling the brakes get failed, and the entire railway get out of the track, and almost more than 1,000 people lost their life. Okay, so there are n number of tragedies even in aeroplanes. If there is a failure in the electrical and electronic system, you don't have any other choice. Your plane get crashed. Okay, means what? We have to ensure that whatever the electrical or electronic system we are using in the modern days, the failure of that electrical or electronic system should not cause an unacceptable risk. And this is what the primary job of the functional safety manager in all companies. And I'm doing the same things. Now the question is how we assure my product is a safety compliance. Okay, so generally in every areas or for every field, there are different standards which guides the development of product according to the safety norms. Okay, so if you check for aerospace field like aircraft or aeroplane, there is a standard DO 178B. This standard has a standard guidelines to design or develop the electrical or electronic systems. Okay, similarly, there is a standard IEC 60880 which is applicable for the electrical and electronic system which are developed for the nuclear areas. There is a standard ISO 26262 which gives the guidelines related to the product development for vehicles on road. Okay, so now when I'm talking about the vehicles on road, It is related to the trucks, buses, cars, and motorcycles. So area wise, you'll find that we are having the different standard, and all these standards provide the guideline related to the development of the product, which should have the safety compliance. Now, here you'll find IC6. Let me take a please. So here you will find the IC 61508. This is the mother standard, and this is the standard for the industrial electronics. So when we are developing any products, product means electrical or electronics products, then what kind of things needs to be considered to make the product as a safety compliance is provided by the IC 61508. Then all other standards adopt the norms provided by the IC 61508 as per their area requirement. Okay, now when we are talking about the VLSI, basically VLSI is developing the chips, and the chips are used in a different domains. Okay, and that's why when we are developing the chips, we need to identify in which area the product is going to use, and accordingly we have to follow the standards. Okay, so we are having the microcontroller which are suitable for the automotive sector. We are having the microcontrollers which are suitable for the nuclear sector. We are having the microcontroller which are suitable for the medical sector also, because all the sector has their own requirements, and the microcontroller should fulfill that requirements. So the vendor develop their microcontrollers, they use the particular standards and provide these chips to the particular area. Even the companies or organization which are developing the products under these areas, they ensure that whatever the product they are using or whatever the electronics component they are procuring or using for the development of the product, they are having the particular standard mitigation or a requirement applications. Now I will not go in much detail about each standard, but in all these areas one thing is common, that is the safety analysis. Okay, in all this area when you are developing the products, you need to have a safety analysis. So what is the objective of the safety analysis? We have to identify the faults or failures in any electrical or electronic system or component that can cause the violation of safety norms. Okay, so this is the primary objective of the safety analysis. And when I'm talking about the safety analysis are performed during the product development phases. Now we are having the different phases like concept phase, which is a very primary phase. Then we are having the system phase, hardware development phase, software development phase. So these are the different product development phase, and at every phase we have to perform the safety analysis to assure that the product is a safety compliant at every phases. Okay, there are a different safety analysis method. One, based on their approach, they are classified. First one is the qualitative or quantitative. Okay, so when we are talking about the qualitative, so just we are identifying the failures in the product. Okay, but we are not identifying the frequency of failures. Okay, so the frequency of failure can be identified in the quantitative way, because the quantitative way always talks about the number, and qualitative is always talks about the statistics. What we can say that it is a theoretical explanation. The failure can happen because of these kind of faults. Okay, so that is called as the qualitative analysis. But what is the probability of occurrence of failure? That will be dealt by the quantitative analysis. Then what type of approach you are using to identify the failures? Okay, whether you are going from bottom to top or top to bottom. Based on that, we are having the inductive analysis and deductive analysis. So when we are talking about the inductive analysis, basically, so they follow bottom to up, means when there is a failure in a basic component or when there is a fault in a basic component, how it will propagate into the product failure. So the best example is the FMEA, and there is a deductive analysis where we are following the top to down approach. Means if the product fails in this manner, what are the possible causes that can lead the product to fail in this manner? So this approach is called as the deductive approach. So the most popular method which is used as a FTA. Now the FMEA may be a qualitative or quantitative. Similarly, the FTA may be a qualitative or quantitative. Depends. We will see how the qualitative and quantitative methods are considered. So as already told, the qualitative analysis method identify the failures but do not predict the frequency of failures. How much time the product will fail in its lifetime. Okay. So if I want to calculate that data, I need to provide the quantitative analysis. Okay. Now the quantitative analysis method predicts the frequency of failure. Now suppose I am having the random a memory, and the memory has suppose 1000 hours life cycle. So in that, these are the operating hours. That is the 1000 operating hours. In that 1000 operating hours, what is the probability of failure of that memory? How much time the memory gets failed? So that data can be calculated or we can determine using the quantitative analysis. Similarly, the inductive analysis, this is the bottom-up method. So in bottom-up method, basically we start from the known causes and we will identify the possible effect. When I'm going for the deductive analysis, it is a top-down method. Here we start from the known effects. Okay. Now, what is the meaning of known effects? Suppose I'm having an amplifier. So what is the expected functionality of that amplifier from any amplifier? It should amplify the input, but it may not amplify. Okay. So may not amplify is the known effect. Now, when it is not amplifying, then why it is not amplifying? What are the factors that can cause the amplifier to deviate its behavior? So that we need to find out. Okay, so this is from known effect to the six possible causes. So this is the top-down method, and obviously FTA is the one of the most popular method which comes under the deductive analysis. In hardware industry, the reliability block diagram is also used. Reliability block diagram basically talks about the reliability of individual components which are used to build the product. And based on their reliability data, the organization can determine or give the assurance that their product will sustain for 10,000 number of cycles or 10,000 hours or 10 years or 15 years. Okay, so that assurance is calculated by the reliability block diagram. Generally, it is preferred to have the inductive and deductive analysis to increase the coverage. When I'm talking about the coverage, basically it is a fault coverage. Okay, so at every phases, it is recommended that industry should use both inductive analysis and deductive analysis to increase the fault coverage, as well as you must have the qualitative and quantitative analysis for different phases. So let's start with the deductive analysis. As already told, it is top to bottom approach. So work backward from hazard to causes. Okay. So here I am having the event, like as already told, amplifier should amplify the signal. This is what the expected behavior from the amplifier. But if it is not amplifying, so I know there is a wrong behavior. So amplifier may not amplify the signal. So this is the top event, and then I need to understand what are the different causes which can lead to the amplifier not to amplify the signal. Okay, so it is called as the from hazards to the causes. Basically, it is a graphical method that models how failure propagate through the systems. Okay, then they also provide the details how the component failure leads to the system failure. Okay, if there is a failure in one of the transistor, so what is the possibility if the failure in the transistor will that leads to the failure in the amplification functionality. Okay, then it is also possible not all component failure leads to the system failure. See, a system has n number of components, so some components or their failure may not leads to the failure of the entire system. Obviously, there is a degradation in the functionality. Okay, there is a degradation in the functionality, but it will not cause a failure. So I know that my amplifier has a gain of 10. If one of the component gets failed, the amplifier will not deviate its functionality. Instead, it will operate in a degraded mode. What is the meaning of degraded mode? Instead of providing a gain of 10, it may provide the gain of 8 or it may provide the gain of 7. Okay, but it will not cause the failure of the amplifier. Now there is another which is called the inductive method. Now it is one of the rigorous method. So when I'm talking about the inductive method, so it works forward from fall to the mishap. Means what? It is from bottom to the top. So I have to analyze the different components that we are using to build the product. Now that component may be a hardware component, that component may be a software components. Okay, or it may be a combination of both. Suppose I want to build an autonomous system like a traffic light control module. So I know that it has a combination of hardware and software. Okay, so I have to understand what are the components I'm using to build the product, and if that components get failed, then how it is going to affect the system or how it is going to cause the failure of system. Basically, it is a tabular method. Okay, and it is one of the most systematic method because it starts with the component that is the single point failure, and it will give the complete analysis about the failure. As already told, it is one of the rigorous method. And here we are having some templates like atom function. Suppose I am having a device, a product which detect the smokes. Okay, so what is the functionality of smoke detector? Smoke enter assembly. Then what is the possible failure? Smoke does not enter. Now here we will take a detailed overview of this method in a subsequent slides, but this is what the typical tabular method, and basically it is based on the risk priority number. We'll see what is the risk priority number in the subsequent slides. Let's start with one of the most popular method, that is the FTA, that is the fault tree analysis. As it is a deductive analysis, we start from the top and we reach to the bottom. It basically produces a fault tree. Okay, when I'm talking about the fault tree is the logical models. Logical model means what? I'm having some logical gates which represent the relationship of undesired event to more basic event. It has a top event of the fault tree is undesired event. We will see what is the undesired event and all these things. Okay, just keep the terminology or try to understand the terminologies. When I'm talking about the top event, basically it is the event that we are not expecting. As already told, amplifier is not amplifying the signal. This is the top event for the amplifier. Now, when I am talking about the top event, so it is an undesired event basically. Amplifier is not amplifying the signal. This is the undesired event. Then we are checking what are the middle events. These are called as the intermediate events. Means what are the middle components? If that components get failed, the amplifier will not amplify the signal. Then we are identify the bottom layers. What are the components we are using in the bottom layers? If that components get failed, that can cause a failure in an intermediate level, and that intermediate level failures are propagated into the top levels. Okay, so in this way we are building the hierarchy from the top to the bottom. So here we are having the typical structure, like this is my top event. So here I am mentioning the amplifier fails to amplify the signal. This is what my top event. Now, why it fails? So one of the reason may be no supply voltage is available. Okay, or second maybe there is a problem in circuit. This may be intermediate event. Now, when I'm saying no supply voltage is available, so I need to check why supply voltage is not available. It may be the wire which is providing the supply voltage get broken. This may be one of the event, or the switch which is providing the supply voltage is off, or there is a failure in the switch, like that. Now, when I'm talking about the circuit, if there is a fault in the circuit, so what is the fault in the circuit? The circuit is not receiving the supply voltage, like that. Okay, this may be one of the reason, or one of the wire which is connecting the different components in the circuit get broken, or the circuit is not receiving the power supply. This may be the reason. So in this way, I'm starting with the top event, and then I'm going to the bottom, and then I will understand, okay, if there is a problem in one of the component, how the faults will propagated into the failures, which can cause the undesired top event. Now, what is the objectives of fault tree analysis? If you refer any books, there are a number of books on the fault tree analysis, because this is a very popular method. So what are the objectives? They provide the common objective. First, resolve the cause of system failure. Obviously, everyone wants to identify what is the cause of the system failure, and not only the cause, people wants to identify the root cause. Okay, not the superficial cause. They wants to understand the root cause. Then they wants to quantify the system failure. Now, when I'm talking about the quantify, it talks about the number. What is the probability that system get failed in a particular way? Okay. Then once I'm able to identify the cause, obviously I need to evaluate the potential upgrade to the system. How I can upgrade my system so I can replace that root cause, or I can remove that root cause. Sometimes I need to optimize the system also, because I need to put a lot of resources to develop that system. So if I'm able to optimize that resources, I'm able to save a cost on that system. Then sometime a particular system may fail in a particular environment. Okay, so in that case, I need to understand what was the cause which responsible for the particular incident. Okay, so I need to understand. Then there is another objective, that I need to use a FTA to model the system failure in the risk assessment. Okay, if my product get failed, what should be the probable risk, and based on that we can decide whether the risk is acceptable or not. When I'm saying the risk is acceptable or not, means what? I need to understand whether that risk cause any damage, to either a human being or environment, or it cause any physical injury to the human being or a living animals. Now, before starting the FTA, what I need to understand or what things I need to consider. First things, if we start with the top event, we need to move in a clockwise direction. Okay. So what is the top event? Means if I am developing a amplifier, I know that it should amplify the signal. So what is my top event? If it is undesirable event, means what? It is not amplifying the signal. So that is my top event that I need to understand. So that should be my top event. Then existing event. What are the other events that I need to consider? Okay. So existing event means what? Now, many times the people say that, okay, sometime I need to use the particular device as an amplifier, but sometime it should also work as a switch. Okay. Then I need to consider really my device can work as a switch as well as an amplifier. If yes, then I need to consider that existing events also. Like a transistor, we know that the transistor can also operate as a switch as well as an amplifier. So that I need to consider. Then unallowed events. Unallowed event means what? The events that are not related to that device. Okay. So what I'm saying, unallowed event is what? Amplifier needs to amplify the input signal, but what should be the nature of input signal? That is not the boundary of the amplifier. Okay. The signal may be a sinusoidal signal, it may be a square wave, it may be a trapezoidal wave, or it may be a noise. But it is not a job of amplifier to understand the nature of signal. So I need to consider this also unallowed event. Then the physical bounds of the process. Now, what is the meaning of physical bounds? What are the different other components which are connected to my amplifier? Okay, it may be a supply voltage, it may be an input signal, it may be a some what I can say output. The amplifier output is connected to some other circuitry like that. Then the equipment configuration. Now, if equipment configuration means what? For what type of application the particular equipment is going to be used, whether it is used for the military application, whether it is configured for some automobile application, whether I am configuring it for some aerospace application, like that. And if the next is the level of resolution, means what? If there is a failure, how can I resolve it? What is the level? There are different C level, like C level, severity integrity levels. Okay. Uh, so at what level we need to resolve or we need to provide the resolution. So all these things needs to be considered before starting the FTA. Means what? These many things needs to be in hand to build the FTA or to construct the FTA. Now, what are the different elements of the FTA? So basically, there are now, as already told, it is a fault tree methodology. So obviously, it has a wire, it has some gates. Okay, so there are some events, gates, and transfers. So when I'm talking about the events, so these are the different, what we can say, conditions. Okay, events are nothing but the conditions. Then the gates, obviously these are the logic gates, and transfer, the way the signal is passing from one node to the other node. So there are different things. When I'm talking about the basic events, okay, so these are the, when I'm talking about the basic events, basically a failure or error in a system component or element, basic elements. External event, normally expected to occur. External means what? The input signal to the amplifier. That is the external event. Undeveloped event, an event about which insufficient information is available or which is of no consequences. Means what? The input signal is available, but I don't know the nature of input signal. That is the undeveloped event, because I'm having insufficient information about the availability of that signal. The signal may be available or it may not be available. Okay, and if the signal is available, I don't know whether it is a intended signal or it is a noise kind of things. Then there is a conditioning events like logic gates. Okay, we know the logic gates. There is AND logic gates or logic gates like that. So here we are having the different symbols that are used to construct the FTA, like basic events that are represented by this symbol. External event, basically these are the pin symbol. Undevelopment events, these are basically things. Okay. Then the gate symbol. So there are different gates which are used to build the FTA. It may be OR gate, it may be an AND gate, it may be XOR gate. Okay, it may be a priority AND gate, it may be inhabit gate. Now, when I'm talking about the priority AND gate, so when you are developing a product, it is always check that what is the intended functionality of the product. Now, suppose I'm developing a braking system, okay, an electronics control unit which controls the brake. So when I'm developing that ECU, so highest priority is that when user press the brake, irrespective of the sudden task, what is the current state of your ECU, doesn't matter. Your ECU should apply the brakes. Once the user press the pedal or a clutch of the brake system, once that signal is activated, at that time, whatever the situation you have about your microcontroller, maybe your microcontroller is busy to write some data in memory, or it may be checking some other events. But when it receives the input from the pedal, he has to left all other tasks and give the priority to activate the brake. So for this kind of things, we are using the priority AND gates. Now there is a inhibit gate also. Means what? Sometimes we need to restrict certain signals. Means when the clutch system is activated or when the clutch signal is turned on, then all rest of the signal should be inhibited, which can interrupt the microcontroller. Okay, so for that kind of things, we are having the inhibit gate. Then this is the transfer in and transfer out. Basically, it is a what we can say that the transfer gate. Okay, so these kind of symbols are generally used to build the FTA. Now, when we are building the FTA, we need to understand whether my system is a series system or parallel system. Okay, so in a control system, if you remember, we are having a block diagram reduction methodology. Okay, so that kind of logic are also applicable for the fault tree. Okay, so here I may have a multiple block in series. So how can I represent that in a FTA? So obviously this is the OR gate. Why? Because when all blocks are connected in series, if there is a failure in the B element, that failure in the B element can affect the final event because they are all connected in series. Okay. Now, if the elements are connected in parallel or the systems are connected in parallel, it is represented by the AND gate. Means what? To happen the topmost event, all the input should be active. Only in that case, the system will or the top event will occur. So this kind of presentation is called as the series system or this kind of presentation is called as the parallel systems. Now, in any automotive vehicles or in any field, some systems are connected in series and some systems are connected in parallel. Now, here we may have the combination of series and parallel. So how the fault tree is connected? T stand for the topmost event. Okay. So when the system is connected in series, so it is a CCF, it is a common cause failure. Okay. So when I am talking about the CCF, basically it is a common cause failure. Now, what is the common cause failure? I know that for few systems, few signals are common, like power supply. If there is a failure in power supply, we know that all the electronic system needs a power supply for their operation. If the power supply get failed, the entire system get failed. So this is called as the common cause failure. Okay. Now, if the input which is coming to the block A and block B, it is a common. If that input gets failed, obviously block A and block B get failed simultaneously. So this is called as a common cause failure. Now, I'm having the block CCF also. So how this block diagram is converted into a fault tree? So this fault tree is the representation of this block diagram. So CCF, and this is the simple event S, which is nothing but the ending of event A and event B. Okay. Now, here I'm having a small example how the FT is built. It is a very small system. Here, a fault tree distribution, the various event contribute to the flat tire. Okay, means you have a car, and if that tire gets flat, so what is expected? The tire should have the air. So what should be the top event? It is an undesirable event. Means what? The tire gets flat. Means there is no air in the flat. So what are the possible reasons that tire get flat? First one is your road condition. There is some road debris, and that can damage your tire. This may be one of the cause. Or there is a failure in the tire. Now, when I'm talking about the failure in the tire, so what are the failure? It may be a tire is defective, or your tire get extremely hot. Okay, so that kind of reasons may cause the flat tire. Okay, so see here how we are propagating from top to the bottom. Now, the FTA may have the qualitative and quantitative approach. As already told, qualitative approach can find out the failure, helps to find out the failure, or helps to identify the system weakness or system failure. But it will not help, or it will not predict the frequency of failure. So for that, we need to have the quantitative analysis also. Okay, so the FTA may be a qualitative or it may be a quantitative. So the qualitative FTA helps to identify the system weakness or the root cause which can lead to the system weakness, system failure, and quantitative analysis helps to understand the probability of or the frequency of system failure. Now here I'm having a very simple example of the FTA. Generally, we are having a very large circuitry, but just for understanding purpose, I have taken a very small circuit. Here I am having a system which are driving the motor. So my final aim is I need to drive the motor. Okay, maybe in a clockwise direction and or in an anti-clockwise direction. So here I'm having the power supply. Here I'm having the switch, fuse. So when the switch get closed, the path or the circuit get closed, and the current start moving through the circuitry, and it provide the EMF to the motor. So the motor start rotate either in a clockwise or anti-clockwise direction, depends. So this is basically an example of your windows, a car windows. We know that When we press a button, the windows glass get down or it get up direction. So this is one kind of circuitry. Now, here is the FTA. My aim is I need to drive the motor. Okay. But what is the other scenario? Means now I need to understand what is the FTA basically talks about. I know that the motor should rotate in the intended direction, but there is a possibility there is a failure in the motor. Okay. So my top event is motor fails to operate, means it is not working at all. Now I need to identify what are the different cause which can leads to this top event. Okay. So obviously the topmost event is the motor fails to operate. So what is the probable reason? There is a defect in the motor. Okay. This is the one reason. Now defect may be the motor wiring get damaged, or the motor wiring get burned, or there is a mechanical defect in the motor. This may be one of the reason. There is a second reason. I know that to rotate the motor, I need a current. So there is no current to the motor. Now, if there is no current to the motor, then I need to check what are the things which can stop the current. Okay. So first one is the switch is open. If you compare this circuitry, if the switch is open, obviously we know that the circuit get open and there is no current in the circuitry. So this is the one of the reasons switch get open. Or the wires, the intermediate wires which is connected to the motor get broken. So wire is open. Or there is a problem in the fuse. I know that I'm having the fuse. The fuse fails. Means what? The fuse get open. Or there is a power supply failure. So these are the possible failures which can stop the current in the circuitry. Okay. Now again, I need to analyze when switch opens. So what are the possible reasons which can cause the switch opens? The switch failed, means there is some mechanical problem in the switch. Okay. It may be, I can say that whatever the element I'm using in the switch, that element get broke down. So there is a mechanical problem, or the switch opens erroneously. It may be because of some other fault, the switch get open. And these two reasons may cause the switch open. Now, when I'm talking about the fuse fails or fuse get open, so what are the possible reasons? Fuse failure under normal condition. Normal condition means what? There is extremely large current which is flowing through the circuitry and it is higher than the fuse capacity. So fuse get open, but the operating conditions are normal. So to protect the motor, fuse get open. This may be one of the reason. Or fuse fails due to the overload. Okay, overload means what? The motor is demanding much current, which is higher than the normal capacity of the fuse, and it get fails. So now there is an overload circuitry. Why there is overload? There may be a failure in the wire. There is some short circuit, or there is a sudden spike in the power supply. So in this way, we are trying to understand the different faults in the circuitry which can leads to the failure in the system. Okay. Now it is the same FTA which is converted into a different event. Okay. So this is the topmost event. So here P1. So here we are representing what is the P1 defect in the motor. Now here we are giving the probability. What is the probability? What is the frequency of failure of that component? Okay. Probability means what? What is the probability that component get failed? So when I'm saying the P1 defect in motor, what is the probability that motor get or the motor is faulty? It is 0.01 probability. 10% probability means. Okay, that motor is a faulty. Now there is a G1. So what is basically G1? If you check G1, what was that? No current in the motor. Okay. Now, when I'm talking about the G1, so what are the different events that can cause G1, G2, and G3 to happen? Okay. So what is the P2? Wire open. So what is the probability that wire get broke down? 10% probability, because when you are building the circuitry, generally you are selecting the wire which are in a good conditions and has the ability to carry the sufficient amount of current. Okay. Then P3, power supply failure. Obviously, we cannot neglect the failure in the power supply, but it is generally assured that when I am using a supply, it is an uninterrupted supply, but still we are considering the 10% probability. So for every component, we are having the probability. Means what is the probability that particular component get failed? So the question is how we are calculating the probability. So there are different industry standard which provide this data. This probability is called as a failure in time. Every component has its operational life. Suppose I'm considering if I'm using a transistor, I know that the transistor has its own operating life. And based on the reliability data, these standards provide what is the probability that transistor get failed, or what is the probability or how much time the particular transistor get failed in its operating hour. So this is called as the fit value. That is a failure in time, and that fit is the representation. When I am saying 1 fit, so it says that the particular component gets failed 1 times in its operating hour. And what is the general operating hours for any component? It is 1 billion hour. Okay, when you are developing any component or manufacturing any electronics component, it is expected that the component should operate for at least 1 billion hours. In that 1 billion hours, how many times the component gets failed? That value is called as a failure in time. So how that value is calculated? Based on the reliability diagram. Okay, so here we are having the different probabilities for different components. Once we got that data, we built the quantitative FTA. We built the quantitative FTA. Now, based on all this failure data for all the components, I can say that there is a 6.1% probability that motor may not rotate. There is a 6.1% probability that motor may not rotate in the particular system. Okay, so based on that data, here you are having the final probability. So in this way, we can say that in its operating hour, suppose the motor needs to operate for 2000 hours. So in that 2000 hours, this many time the motor may not rotate because of the different faults in the different components. So in this way, we are trying to understand the frequency of failure of a particular product or a particular system. Now there is another concept in the FTA, that is the minimal cut set. See, the system or the products are huge. There are n number of electronics components. And if I'm considering each and every component to understand the faults, then it is very tedious job for the person to consider all this fault or to understand all this fault. So generally we are considering the minimal cut set. So what is the minimal cut set? This present the minimum faults that can leads to the failure of the system. As already told, not every fault in the system leads to the failure of the system. Okay, but there are certain faults that needs to be considered which can cause the failure in the system. That faults are called as the minimal cut set. Okay. Now, how we can calculate the cut set, minimal cut set? So there are two methods. Either we can go for the Fusel and Wesley methods or Boolean rules. And Boolean rules are very popular to calculate the minimal cut sets. Basically, they are based on the set theory. Okay, they are having the interception and union concept. So the Boolean rules are very popular to calculate the minimal cut set. So what is the advantage of minimal cut set? Basically, it gives the set of minimum faults that needs to be considered to understand the system failure. Okay. So now here I am having one FTA. Okay. So here I am having the top event. These are the intermediate event, and A, B. These are the different conditions. If that components get failed, there is a failure in the system. So here I am having this one of the FTA. So we know the Boolean rules. So it says that A plus A is A into A is A. We know that in Boolean we are always representing A with either 0 or 1. Okay, it is a binary system. Similarly, there is a law of absorption, like A plus A dot B is nothing but the A, and A into A plus B is nothing but the A. Now, for this FTA, I want to calculate what is the probable combination of faults that can leads to the top event, or that can leads to the failure of system. Then this is how the system is solved. Okay, and then I come to know that the minimal cut sets are A dot C, A dot E dot E, B dot C, and B dot D dot E. Now, what is the meaning of this? The fault in A component and the fault in C component occurs same time if the faults in A component, and it is not OR condition, and the fault in C component occur at the same time. Only in that case it causes a failure of system. Okay. Similarly, the fault in A component, D component, and E component occurs simultaneously at a time. Only in that case it leads to the failure of system. B dot C says that the fault in a B component and C component occurs simultaneously. Only that can lead to the failure of system. So this is the prediction. Okay. Now, based on this data, I can understand what kind of failure is occurred, and once I get that, which fault leads to the what type of failure. Okay. So this is the way to understand what are the minimum fault, or what are the fault that can leads to the system failure. Now here I am having the Boolean algebra for the pump fail. Okay, there are different systems which are using the pumps, and then if I use this concept, pump fail concept, so it says that if there is a fault in M system, if there is a fault in an M component, that can lead to the failure of pump system. Okay, if there is a fault in W and Z component, if there is a fault in a W and Z component simultaneously, only in that case it leads to the violation of, or it leads to the failure of system. In this way we can interpret the FTA. Now, though it is one of the popular method, the FTA has a certain disadvantage. First, it is a enormous because we are having the n number of components in a system. So we have to use thousands of logic gate and intermediate event. Okay. Now, not necessarily all failure modes are considered. As already told, we are always going for the minimal cut set. So in minimal cut set, we are getting the minimal components which tell us if that component get failed, there is a failure in the system. But sometimes there may be a failure in individual component that leads to the failure in the system, which is not covered in the FTA. Now, when we are doing the FTA, this is one of the most important condition. You should have a knowledge of the system. Without that knowledge, you cannot build the FTA. Okay, so you have a rigorous experience as a system engineer. Then it assumes that hardware not to fail partially. Now, what is the meaning of that? If hardware fails, it should fails completely. The partial failure in the hardware are not considered in the AFT analysis. Then the assume failure of one component does not put stress on the other component. This is what general consider in the FTA, but this is not the true condition. We know that if one of the component gets failed in a short circuit mode, it causes excessive current, and that excessive current may put other component in a stress condition, or it can increase the burden of the next component. But these kind of things are not considered in the FTA. Then the external event not correctly treated. External event means what? The external conditions are not considered when you are building the FTA. External conditions is what? The environment in which your products is going to be fit, or the environment in which your product is going to be sold. See, different companies develop different product for different regions. The products which are sold in India has a different specification for the same product which is sold in the US and UK. Why? Because they are having a totally different environmental factor, totally different human operating factor, totally different what we can say that the operating conditions, which are not considered when we are building the FTA. And these are the major disadvantage of the FTA. Now, certain disadvantage of the FTAs can be overcome by adopting the failure mode and effect analysis methodology. Okay, so basically it is a inductive analysis. So when I'm talking about the inductive analysis, we're starting from bottom and try to reach to the top. Okay, so now if we consider the same example here, okay, now here I'm having the same circuitry. So what I will do, first of all, I will analyze what are the different components used in the circuit. I may have a power supply, switch, fuse, wire, and motor. Now, what is the intention of the circuitry? To drive the motor in the particular direction. Now, what I will try to understand in FMEA, I will select the power supply. Now, try to analyze the different failure of power supply. What is the meaning of failure? If there is an instability in the power supply, then what will happen with the motor? If the power supply get over voltage, okay, in case of over voltage, what is the impact on the motor? In case of under voltage, what is the impact on the motor operation? So in this way, I'm trying to understand. Means what? I'm starting with the individual component, their failure, and trying to understand their impact on the motor. Now, if I'm considering the switch, if the switch is open, what will happen with the motor? If the switch is not close properly. What is the meaning of close properly? Yes, this is touch with this, but not with the full capacity. Then the fuse. If the fuse is not working properly. Now, when I'm talking about the not working properly is what? If the fuse get open, if the fuse get lower current, higher current. So here I'm having the different component and their failure, how their failure leads to the system failure. That is the part of failure mode and effect analysis. Okay, so the failure in a component, how the failure in a component can leads to the particular undesirable event. So that is covered in the FMEA. So here we are having the different terminology. When I'm talking about the failure, basically it is a loss of intended function of the particular device under the stated condition. So I know that the motor should rotate when the power supply is available, but it is not rotating, so or it is not moving, so it is a failure in the motor. Failure mode. A failure mode is what? The manner by which the failure is observed. Now suppose I am having the resistor. So in which way resistor get failed? The resistor get open. This is one of the failure mode. Or there is a drift on the resistor. Drift means what? The resistor value get changed. This is one of the failure mode. Okay, so in this way I need to understand. If I'm talking about the power supply may fail. It may be over voltage condition. This is one of the failure mode. Under voltage condition, this is another failure mode. The instability in supply voltage, unstable supply. This is the another failure mode. So I need to consider all the possible failure mode. Failure effect. Immediate consequences of failure on the operation, functional or functionality or status of some item. If the power supply has over voltage, what is its impact on the motor? So that is called as the failure effect. If the power supply has an under voltage, how it affects the motor? If there is instability on the supply voltage, how it affects the motor? That is called as the failure effect. Then the failure causes. Now, when I'm talking about the failure causes, basically these are the defects in the design, process, quality, or a part application which are underlying cause of the failure or which initiate the process which leads to the failure. Okay, so failure causes means what? What are the different causes that can lead to the system failure? Now, the severity. This is important aspect. When I am talking about the severity, when the particular system gets failed, what will be its impact? Now, impact, it may be with respect to human life. Impact, it may be with respect to economic aspect. Impact, it may be with respect to brand value. In fact, it may be with respect to reputation. Okay, so what will be the impact of this failure on these different aspects? So that is called as the severity. So when I'm talking about the FMEA, so it has three main phases: severity, occurrence, and detection. Now let's try to understand in a simple way. I know that I want to drive the motor, so I have a power supply. So the power supply has three failure mode: under voltage, over voltage, and continuous fluctuation in supply voltage. Now, first of all, what I need to check, what is the probability of occurrence of that failure mode? Okay, what is the probability of occurrence of that failure mode? That comes under the occurrence. Okay, so what is the probability that there will be the over voltage? What is the probability that there will be the low voltage? What is the probability there will be oscillations in the supply voltage? That I need to check. That comes under the occurrence. When the particular failure mode occurs, what I need to check, whether I am having any mechanism to detect that failure mode. Okay, whether I'm having any mechanism to detect that failure mode. If there is over voltage, so that over voltage may cause a overcurrent, so my fuse is there. Okay, so I'm having certain things to detect that. And then what will be the severity? Means if the failure occur, what will be the severity? So based on that, we are having the different aspect. Okay, so this is the just theoretical explanation of what I just told you about the different scenario. Now for each parameter we are having the different rating from 1 to 10. Okay, when I'm talking about the severity, 1 means no effect, it has no impact on the functionality, or it has no impact on the human life, it has no impact on the economy, brand value, or reputation. 2, very minor, very minor. 3, minor. 4, 5, 6, moderate. 7 or 8, it has a high severity. Okay, high severity means what? There is a threat to the human life, or human can lost his life, or if the particular failure occur, it can cause a huge economic damage to the company, it can cause a huge damage to the company reputation, it can cause a huge damage to the company brand value. So that comes under the 7 or 8. 9 or 10, what do you mean by very high and hazardous? Means what? If your product gets failed, the company has to file the bankruptcy, or the company has to close their operation. That is the severity. Okay, occurrence, again same, we are having the parameter from 1 to 10. Like 1, like no known occurrence or similar product or process. 2, 3, relative very few occurrence. 4, 5, 6, moderate occurrence. 7, 8, high occurrence. 9 and 10, very high occurrence. Okay, so I can say that when I'm having 9 or 10 rating for the over voltage condition, means what? The over voltage condition may occur repetitively in the life cycle of that device. Then the detection. What is the probability that I can detect the failure mode? 1, that is the certain. Means what? The fault will be caught on the test. 2, almost certain. 3, there is a high probability that I can detect the fault. 4, 5, 6, moderate. 7, 8 means what? I don't have any mechanism to detect that fault. And 9, 10 means what? I doesn't have anything, so I can detect that fault. So fault will be easily passed, even the customer get undetected. Okay, so that kind of things. Now based on that, we are having the RPN number. So what is the RPN number? Basically it is a risk priority number, and it is the product of severity, occurrence, and detection. It is a product of severity, occurrence, and detection. Now based on that RPN number, customer has to take the call, or the organization has to take the call whether they want to release the product, whether they want to release the product. So here I may have the example. I will just give the example here. See here. So here I am having the RPN number. Now when the RPN number is very high, so the company has to think how I can reduce that RPN number. If I am not able to reduce that RPN number, I need to have the agreement, like legal agreement, or what we can say that ethical agreement with either government or the customer to release that product. So the RPN number is a very critical number in the FMEA. There are different type of FMEA. The FMEA which are talking about the manufacturing process or assembly process. These are called as the process FMEA. The FMEA, which are generally dealing with the design analysis, these are called as the design FMEA. Basically, we are interested in the design FMEA, system FMEA, software FMEA. Being an electronics engineer, we are dealing with the different type of FMEA. As already told, when I'm talking about what is the use of FMEA, basically it helps to identify the faults in the component which can lead to the failure in the system. And if we are in advance, if we are able to identify this, it will save a huge cost of the company, reputation of the company, brand value of the company. And these are the few theoretical aspects which can talks about the different usage of the FMEA. These are the few advantage, like it helps to improve the quality, reliability, and safety of the product which are going to release to the customer. It helps to reduce the system development timing and cost, because if in advance I am able to understand the error or bugs in the system, I can minimize them and reduce the redevelopment cost. Okay, so these are the few advantage provided by the FMEA technology. So here I'm having a simple example for the FMEA, which is a smoke detector. Smoke detector is a device which is commonly used in all the organization. Okay, it is one of the safety features. So what is the input to this? Presence of the smoke, if the smoke is present. And what is the process? How you are going to process the smoke. So the smoke enter into the assembly, smoke into the chamber, then smoke passes to the detector. There is an ionization chamber. Then we are converting the smoke into the equivalent voltage, like that. And here we are having the outputs like successfully capture the smoke, then light is activated, and then the alarm sound. So these are the outputs. Now, based on the different SOD values, we are calculating the RPN numbers for the products. And based on that RPN, we can understand what are the situations or what are the incidents which can cause a higher RPN number. And then we need to understand how we can reduce the RPN number in the particular situation or at a particular incident. So this is the typical structure of the FMEA. We start at the system level, or we can start with the lowest component, then at the intermediate component, then the subsystem component, and then the final system component. Means how the failure in one component can lead to the failure in the system. Now, as already told, generally the FTA and FMEA are used in combination because we need to increase the fault coverage. One is the top to bottom and second one is the bottom to top. And generally these are combinedly used in every phase of the product development. So this is all about the safety analysis method which are used for the different problem analysis. If you have any question or any query, please let me know.
Yes, participants, are there any questions? Hello? Yes, I think no questions are there, sir.
Okay.
Yeah, it was a really wonderful session, sir.
Thank you, ma'am.
Deepali, madam?
Yes, ma'am.
Yeah.
Very nice and engaging session, sir.
Just,
And on behalf of
sorry
all
to
of
disturb you, ma'am. We need to take one snap with all the participants.
okay, sir.
Yeah. I request all the participants to uh, switch on the camera. Sir, can you stop sharing your screen?
1 minute.
Participants are requested to switch on the cameras. Thank you. It's done. Please, ma'am, you can continue.
Okay, thank you, sir. Uh, Thank you so much, sir, for delivering this engaging session. And on behalf of all of us and our ANTC department, I extend our heartfelt gratitude to Dr. Amit Kumar Khade, sir, for his enlightening session on safety analysis for integrated circuits. Sir, your clear explanations, practical insights, and various examples from the vast experience of yours have made this session truly vulnerable. We appreciate the time and effort you take to share your knowledge with us. And thank you, sir, for engaging in this impactful session. And we look forward to learn from you again in the future as well. I thank all the participants as well for their attention and participation. Thank you so much.
Yes, sir. Thank you for
Thank
finding the
you.
time actually. After working for a full day in industry and then you're finding out the time for us during this time. Actually, it is very hectic.
Yeah,
job.
actually, I love, but now my job profile is totally different.
Yes, sir.
Yeah,
It's 7:30 to 9 means it's quite hectic for
yeah,
you
yeah.
also. Yes,
Yes.
thank you so much for
Thank you.
engaging
Thank,
session. Yes, thank
thank
you.
you. Thank you for appreciation. Yeah.
Yes, sir.
Ma'am, can I leave?
Yes, yes, sir.
Yes,
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 sir.
sir.
Yeah.
Yes,
Yeah.
thank
Thank
you.
you. Thank you, ma'am.
Yeah. Thank you, sir.
Thank you.
Yes, participants, we are sending again links of both the sessions. So please use that links for giving the feedback.
Just I'm putting it, ma'am.
Yes.